Good morning everyone. Hope you are doing fine. Today we will discuss an important topic of modern algebra, that is homomorphism and embedding of ring. Okay, so moving ahead, this is one of the most important topic of modern algebra and it is very conceptual. Okay, so please try to understand the concept rather than memorizing it. Okay, I always say that modern algebra is the most difficult part of all your UPSC syllabus, and this is one of the difficult part in it. So please try to understand that. And I told you, modern algebra could be done easily with the basic understanding, knowing of those basic definition. I've told this in my earlier videos also. Okay, so today we'll understand the concept of quotient rings. Okay, so quotient groups you have studied. So first of all, let me tell you about that. Okay, suppose we take a group of integer with a, that is z, we pronounce it z, but it is pronounced as z. Okay, and we take another group that is 5z. What will be this element? -5, 0, sorry, -10, -5, 0, 5, 10. Okay, so okay, so all the multiples of z, 5 in z are, suppose this is a group, and it can be easily shown that this is a normal subgroup. This is a normal subgroup. Okay, you all know what is normal subgroup. Okay, normal subgroup, if you are not knowing it, I'll tell you here also. I've taught you this in the group section, but I'm revising it with you since it is an important topic and I found that students find it difficult to understand. Okay, suppose if I take, suppose that this is z. Okay, suppose this rectangle shows z, all the integer. Okay, so if I say that this is 5z, okay, this is 5z. Okay, what if I plus 1 to all? What will be this? This will be, if I have, this will be -9, -4, 1, 6, 11. Okay, so this is a whole another set of group. Okay, so if I say 5z plus 2, this is called coset. This is not group or subgroup. This is called coset. Coset of the subgroup 5z with respect to z. If I add this, okay, what if I add 5z plus 2? We get another 5z plus 3, another, and 5z plus 4, and 5z plus 5 is 5z only. Okay, so if I write this, these are called the coset. In fact, this itself is a coset. This is 5z plus 0. This itself is a coset. Okay, so a normal subgroup is, suppose this is a subgroup, if this is a normal subgroup, if its right coset and left coset is equivalent for all the coset, all the right coset are equal to left coset. That is, if I say that 5z plus 1 is this set, then what is 1 plus 5z? 1 plus 5z. This is itself the same group. So if we see for all this, 5z plus 2 is equal to 2 plus 5z. So all the right cosets are equal to left coset. Then that is called a normal subgroup. In this case, 5z is a normal subgroup. Okay, so first of all, understand the technique of coset. What did we do? We divide z into, suppose this is 5z plus 1, this is 5z plus 2, this is 5z plus 3, and this is 5z plus 4. So we divide a group using the subgroup and we divide into coset. We divide the original parent group into coset. Okay, we divide it as a quotient. See, all the numbers would come in this 5z plus 4, 5z plus 1, 5z plus 2, 5z plus 3, 5z plus 4. So these are called coset. And if these two cosets are equal, then it is called normal subgroup. Okay, now comes the technical part. See, why do we do so? We do so because by understanding the properties of this 5z and properties of this quotient, we could understand the whole integer. So in modular arithmetic, what a technique was used, in modern algebra what we use, we try to divide that group so that we have easy to understand the properties of that subgroup or the quotient. Okay, so now let's get to our basic, what today we have to study. Okay, now it says that let R be a ring and let I be an ideal. Okay, so the way normal group behave in the case of the group, similarly I behaves in the case of the ring, ideal. Okay, let I be an ideal. Okay, and then since I is an ideal, then by the basic definition of ideal, if A comma B belongs to I, then A minus B belongs to I. We find that I is a subgroup. We find I is a subgroup of R plus C. Ring is made of two composition, that is plus and dot multiplication, and we know that R plus forms a group and R dot forms a semi group. So it says that if R plus is a group and R plus is again is abelian, it forms an abelian group in a ring, then I will be a normal subgroup of R. Since it is abelian, then I is a normal subgroup, thus we can say that Ry is a quotient ring, quotient group. Now we understand a different concept, that is the quotient group. See, in the previous example, what if I tell you this 5z plus 1, this 5z plus 2, this 5z plus 3, and I consider this whole set as an element. Are you getting this? See, this is a bit tricky and complex, but you have to understand this, that suppose if I consider this as an element, this as an element, this alone, this whole set as an element, and taking these all things together, we form a set, that is 5z plus 1, 5z plus 2, 5z plus 3, 5z plus 4. Okay, then this whole set again forms a group. It follows the properties of group, which are that it is closed. Okay, you can see that if I add 5z plus 1 plus 5z plus 2, okay, suppose I add these two elements, okay, this is 5z plus 1, okay, and if I write 5z plus 2 would be minus 8, minus 3, 2, 7, okay, and 5z plus 3 would be minus 7, okay, and minus 2 and 3 and 8. Okay, so if I add these two, okay, so we get this 5z plus 3. Adding means 5z plus 2, if I add those groups, suppose if I add both of these elements, the resultant will lie in this element only. Minus 4 plus minus 3, this we get minus 7. Okay, if 1 is added to 7, we get 8. If 1 is added to minus 8, we get minus 7. So if all these elements are added to random in any order, we get the same group here. So 5z plus 1 plus 5z plus 2 gives 5z plus 3. So it is a closed. This is closed. We have an identity here, 5z. It is itself an abelian. Since 5z plus 1 plus 5z plus 2, we can also write z 5z plus 2 plus 5z plus 3. This is identity element. See, if you add 5z plus 5z plus 1, if we add these two groups, what do we get? If I add minus 4 and minus 5, we get minus 9. The same group, 5z plus 1. If I add 5 plus 1, if I add 1 plus 5, we get element 6, which is in the same group. So it acts as an identity. It is also, every element has an inverse. Also it is associative. So we can say that itself forms a group. And if this type of group is called as quotient group or factor group. Okay, so what are we doing here? Suppose if we take this in the general form, that is, if R is an abelian group and I be a normal subgroup, and if we collect all the coset formed by the I, that is, all the coset formed by the I, that is R plus I, where R is a belongs to the parent ring or parent group, then this is set of all the coset in I. What is a quotient group? I told you what is a quotient group. You understand the quotient group, you will understand the quotient ring. Quotient group is collection of all those coset with respect to a specific group, and it is denoted by, suppose G is a group. I erase this. Suppose G is a group and N is its normal subgroup, then all the coset formed by N, and if we consider them each coset as an element and we form in another group using those elements, then G by N is called quotient group or factor group. Okay, so in the case of ring which has two operation in it, okay, that is R plus N dot, and we only consider the R plus, that is the group, R dot is a semi group, and R plus we form an abelian group, and we consider this I as a subgroup, then all the quotient, set of all the cosets in R of I in R is called quotient ring. In the case of group, it was group. In the case of ring, it is called quotient ring. I hope this is clear to you, because this is a very important concept, and I have seen almost every student having difficulty in understanding this. They usually memorize it. Okay, they don't get the grasp of the concept of what is this R plus I. This is R by I. This is a collection of all the coset. This is not a collection of elements of R. This is collection of all the quotient in R. Okay. Set of all coset of I in R, then R by I is called quotient subgroup. Okay. So I'll show that if I take in general R by I, where R is a ring and this is a quotient group, where this denotes what it denotes? It denotes the number of all the collection of all the cosets formed by it. And you don't ask me this is a right coset or left coset, because quotient group is only formed if and only if I is a normal subgroup. And for normal subgroup, by the definition of normal subgroup, a normal subgroup is a subgroup whose right and left cosets are equal. Okay, so now I claim that this is a group. Okay, so for this is a ring, or I would say this is a quotient ring. So this is a ring. I claim that this itself is a quotient ring. I claim that this is a quotient ring. So you must be wondering, or you must be thinking that if this is a quotient ring, then what are the operations? See, I told you for a ring is a set with two operations, plus and multiplication. Then how do we define addition and submultiplication did? So this is very simple. Suppose R plus I is an element of this for R belonging to, okay, and another element to this is S plus I, where R comma S belongs to R. This is one coset, this is another coset with respect to I, and I define the addition here to be R plus I plus S plus I. This is equal to R plus S plus I. Okay, and product to be R plus I, any element of this quotient ring into S plus I is equal to RS plus I. I defined the operations which are the addition and the subtraction as r plus I plus s plus I is given by r plus s plus I. This is normal addition in the ring, and r plus I into s plus I, this is rs plus I. I defined it like this only, and it is well defined. You don't need to prove this. I can prove this, but no need for your examination. It can be proved that it is well defined. I can show you how to prove it is well defined. For addition I can show you, and multiplication you can do it by yourself. For better understanding, it won't be coming in your examination. Okay, suppose r plus I is equal to r dash plus I, and s plus I is equal to, okay, another concept here. See, this is the only way where we define the operation we have taken is well defined. Okay, what do we do is we take two equal element and we show that if r plus, okay, I'll show you and then I'll explain you. Okay, if r plus I is equal to r dash plus I, then r minus r dash will be equal to, belongs to I, and s minus s dash belongs to I. Okay, so we can say that r minus r dash is equal to a and s minus s dash is equal to b for a comma b belonging to I. Okay, and r is equal to a plus r dash and s is equal to b plus s dash. Okay, this is clear. I have taken r plus I is equal to r dash plus I, and r minus r dash will belong to I, and s plus I will belong to s dash plus I. S minus s dash will belong to I, and suppose this is equal to a and b, and where a comma b belongs to I, then r, what is the addition I have defined here? R plus I plus s plus I. Okay, this is equal to, for r we can write that a plus r dash plus b plus s dash plus I. Since a, b belongs to I, then a plus b, this could be written as r plus s dash plus a dash plus b dash plus I. Since a plus a plus b plus I. Okay, and all this element is equal to I, since a and b and a and b also belongs to I. So a plus b plus I is equal to I. There I is I told you I is an ideal. What does I here signify? I here signifies is the ideal, all the element of that ideal. So this would be equal to r dash plus s dash plus I, and by the basic definition of this could be written as r dash plus I plus s dash plus I. Okay, so we showed that if I have taken r plus I is equal to r dash plus I and s plus I is equal to s dash plus I, we can show that r plus I plus s dash plus I is equal to r dash plus I plus s dash plus I. So this is well defined. For any, in future also, when you study homomorphism, when you are going to prove first fundamental theorem of group homomorphism or ring homomorphism, you have to show that the addition which you have taken is first of all well defined. Or in the Cayley's theorem or Lagrange's theorem, where you have proved, no, in the Cayley theorem, okay, where we proved that every group is isomorphic to a subgroup of a permutation group. So there also we showed that what the operation we have taken is well defined, and for showing the well defined is very important. It is very easy. What do we say? If I say, in any case, see, if you take a comma b belongs to any, if you say that a, it is, what I say, I'll explain. It is like a opposite of how you prove 1 1. In the case of 1 1 function, what do? You first take fx1 is equal to fx2, and then you prove that x1 equal to x2. In the case where you have to show that addition is well defined or your operation is well defined. You have to show that if you take x1 is equal to x2, then f1 fx1 is equal to fx2. Okay, moving forward, you will learn how to do this, but I would say this wouldn't come in your examination. I have taught you this for clearly understanding the concept. What you have to understand, which you can't leave it, is that what is the meaning of coset and what does this quotient ring signifies is. Quotient ring says that it is a collection of all the coset made by the I. Okay, and quotient ring, for this I have defined an operation. What is the operation? It is R plus I. If I take two elements of this, it will be form of R plus I and S plus I, where R comma S, R plus S plus I, where R comma S belongs to R, and the multiplication operation is defined as R plus I. Okay, so I hope now this is very clear. I'm giving a little too much time on that because it is difficult and students find it. What I have seen in my phase of preparation and what I see my other fellow aspirants or fellow colleagues, or I have seen students, what students have learned. I have always found that this topic, they found it very difficult. Everyone finds it very difficult. Okay, so nothing to worry about that. It isn't a difficult topic unless until you understand it. Okay, if you memorize it, modern algebra is going to be nightmare for you. But if you understand the basic concepts, it is very easy. It is doable. I would say not easy, but it is doable. Okay, so moving ahead. Now what we see is homomorphism. Okay, homomorphism is nothing. Homomorphism is a function is said to be homomorphic or homomorphic if it satisfies some properties. Okay, and we'll see what are those properties. It says that if R plus dot and R dash, and the function here defined, this operation defined is star and operation O by O, if these two are two rings, suppose it says that if R plus and R, these are two rings. Okay, then a mapping theta, I told you function from R to R dash is called homomorphic if it's satisfied these two properties, that is theta A plus B is equal to theta A operation theta B and theta AB is equal to theta A operation theta B. This is called homomorphic. Okay, what do we do? Here, see, this is a mapping from R to R dash. Okay, a function where the domain is R and the range of it is, or we can say codomain or range, whatever you say, it is R dash. Okay, and it says that if A plus B, and this plus here, see, note this plus and this operation, this plus will be for this ring since A comma B will belong to R, and what will be theta A? Theta A comma theta B will be belonging to R dash. Okay, it's very clear since it is a mapping from R to R dash and A comma B belongs to R, then theta A theta B belongs to R dash. So it says that theta times A, theta function hai, so theta A plus B is equal to theta A operation theta B, and theta AB is theta A operation theta B. See the difference of operation. Here the operation is from the first ring, that is plus, and here is the dot. Okay, and in the second we have the star and this operation. Okay, then this is called ring homomorphism. Okay, since in future also we will see that for your understanding I have taken this to different, connotation different, but in the long term I will only show plus and dot. That is theta A plus B is theta A plus theta B, and theta AB is theta A dot theta B. The one thing you should note is in this case this plus is the operation of R, the domain side. Okay, and this dot which is not here, this multiplication is of the domain side, and this plus and this dot is from the range side. Okay, this is clearly understandable. Okay, since theta A will belong to R dash and theta B will belong to R dash, so the operation will be used from also will be from R dash, and here A and B belongs to R, so this operation will be also from this only. Okay, I'll show you an example here. I'll show you an example here. Suppose okay, suppose nothing new or simple, which you will all be knowing. Suppose I consider a function. This is complex number, C to C. Okay, then addition and product of both sides would be same only. Okay, and I tell that f a plus ib, this is equal to a minus ib, where a plus ib will belong to C, and also this also belongs to C. In this case we have taken both C and this the same. Okay, so what do we do here? What do we see? I am asking, my question is this homomorphic? Is this function homomorphic? Clearly we have to check this. If I take a plus ib comma C plus id belonging to C, then f of a plus ib plus f of C plus id. Okay, what will be f of a plus ib? This will be a minus ib, and this will be C minus id. This is equal to a plus C minus I b plus d, or this could be written as f of a plus C plus I b minus plus d, or it can be written as of a plus I b plus f. Sorry. Okay, so it is a plus C. Now this could be written as f of a plus C plus ib plus d. Okay, and this could be written as f of a plus ib plus C plus id. So we can see that the one property it holds, that is f of a plus ib plus f of C plus id. This is equal to f of a plus ib plus C plus id. It follows the property, that is f of a plus b is equal to fa plus fb. Okay, it follows this. So one thing is, for another till now we can't say that this is homomorphic. For this to prove that it is homomorphic, we have to prove another property, that is f of a plus ib into C plus id. We have to show that this is equal to f of a plus ib. Okay, going by the same process, and you know the function, you will easily get to this. Okay, so you do it as your homework and let me know if you are able to do this. So this was an example of this. This is what homomorphism is. Okay, so moving ahead, we have another definition here. Suppose f from R to R dash be a homomorphism. We define kernel of f. Another property, another set, kernel of f is x belonging to R such that fx is 0. All those property, all those element belongs to kernel of f. ठीक है, all those x for which fx is equal to 0 dash. Why it isn't 0 dash? This is an identity element of course I told you, identity element of R dash. Clearly fx would be, see, the function is defined from f R to R dash, so x would be from R and fx would be from R dash, and if this for all those x, if I take all those x such that fx equal to 0 dash, then this is called kernel of f. Suppose in this case, in the example which we are solving, I told you this is a function, and what is kernel of f? What do? We find first all those x. This property of kernel is very important in the linear algebra also. And Dirac theorem, easy question, a very easy topic. Rank nullity theorem is proved using this. Okay, so all those theorems are proved using in the linear algebra using the concept of kernel. Okay, so what do we do here? If I told you, if I take fib is equal to 0 dash. Okay, in this case 0 will be 0 plus 0i. The identity element of the complex number is 0 plus 0i. This is a minus ib is equal to 0 plus 0i. We see that a is equal to 0, b equal to 0. So the kernel of f in this case, kernel of f would be only one element, that is 0 plus 0i. Okay, understood? Understood? It is very simple. We see that what is kernel of f? If f is a function, or homomorphism from r to r dash, homomorphism. See, f is a function, then it is a homomorphism, then it satisfies two more properties. And if for all those x such that f dash is equal to 0 dash, then this is called kernel f. This is a set of all those elements. And now the question here which comes in your examination is prove that kernel of f is an ideal of R. Basic, clear. I told you modern algebra is too easy if you understand the definitions, basics clearly. Okay, so what do? We have to prove that kernel of f is an ideal. Okay, we have to prove this. Okay, for an ideal, let's get back to basics. What do we understand? I is ideal if it satisfies two property, that is, if a comma b belongs to I, this gives a minus b belongs to I, and another property is a r belongs to I for r belonging to parent ring R. I is an ideal of R if these two properties hold. So I have to show that first of all, kernel of f would be ideal of which ring? Similarly, kernel of f has an element from this ring. So we have to prove that kernel of ideal is a ring ideal of R, where f is a homomorphism from R to R dash. So how do we do? The basic understanding. We first take two elements in I and prove that a minus b belongs to I. So first we take two elements in kernel f. Let x comma y belongs to kernel f. Okay. Then by the definition of kernel, fx would be equal to 0 and fy equal to 0. Okay. We can also say that fx minus fy would be equal to 0. Okay, or we can also say that fx 0 dash, I would say that since 0 dash is identity of r dash. Okay, so this will be 0 dash. Now fx plus f of minus y is equal to 0 dash, or this is equal to fx minus y is equal to 0 dash. Since f is homomorphic, this is the basic definition of what I do for studying modern algebra is I understand the concept, basic concept and definition very clearly. I in fact memorize all those definition and then I use in the question. If you know the basic, no matter what examination, whatever the question is, you know how to do that. I will only use the basic definition to prove that kernel f is an ideal of R. See, this is f is homomorphism, so this would come inside. So xy is equal to 0 dash, that means x minus y also belongs to kernel f. So the first property for proving that I is an ideal is that a comma b belongs to I if, then it shows that a minus b belongs to I. We have done this. I have taken x comma y to be two random element of kernel f, and I have showed that x minus y also belongs to kernel f. So first property is, now second property is, if A belongs to I and R belongs to capital R, then AR belongs to I. Okay, we'll do that. What I do, I take X belongs to kernel F. Okay, and R belongs to R. What I have to show that XR also belongs to kernel F. This is what my aim is, to show that kernel F is an ideal. Okay, so what do we do? Since X belongs to kernel F, then Fx equal to 0. Okay, so we can say that f of XR is equal to f of X. Since f is a homomorphism, basic definition of homomorphism, and we know that Fx is equal to 0, this is the 0 dash, sorry. Since 0 is the identity, it is the identity inverse, identity element of 0, if XR belongs to 0, then XR will clearly belongs to kernel F. This was our aim. So which shows that kernel F is an ideal. Okay, so suppose this is ideal, then in the later terms you will be understanding that we will form another quotient group, that is R upon kernel F. And what will be that property? You please think over it. Okay, don't use any book or any YouTube video to understand this. Just try to understand that if kernel of F is a ideal, then there would be some R by kernel F would be a quotient ring or not, and if yes, then what would be its element? What would be its property? Just use any group and find its kernel, find any function, find its kernel, and try to self understand this, analyze those properties of those. Okay, so this is kernel. This question comes in a 10 marker in your examination to show that kernel F is an ideal. Okay, and now there's another thing, that is theorem is kernel F is identity if and only if F is 1 1. If and only if F is 1 1. Okay, F is 1 1. We have to show that. We suppose that F is 1 1. We have to show that kernel of F doesn't contain any element other than 0. Okay, for this you first have to understand that here 0 belongs to R, is identity of R, additive identity of R, and 0 dash is identity of R dash, additive identity of R dash. Then if I say then it can be easily seen that F0 is equal to 0 dash. It can be proved using any of those theorems. It is very easy to prove that. Suppose if I take Fx plus 0 is equal to Fx plus F0. Okay, clearly. So Fx, this is Fx plus F0, and we write Fx plus, it can be the 0 dash, since F dash is a, Fx is a element of R dash, so 0 dash is the identity, so we can add it, additive identity. It won't make any change. Using left cancellation law, we can show that F0 is equal to 0 dash. Okay, so it is given that F is 1 1, then clearly, and we have shown that F0 is 0 dash. So if I say that Fx is equal to 0, F0 is 0 dash, I say for I show that f is 1 1. If I say fx is equal to 0, x belongs, no, this would be, suppose x belongs to kernel f, okay, then fx is equal to 0. Also fx would be equal to f0, and since it is a 1 1 function, then x is equal to 0. So if I take any x belonging to kernel f, we get x equal to 0. That is, kernel of f contains only one element, that is the additive identity of the ring R. Since f is 1 1 and fx is equal to 0 dash, okay, since x belongs to kernel f, then fx will be f0, and since f is a 1 1 function, x is 0, and this will get the answer. And to prove it conversely, suppose kernel of f has only one element, that is 0. Okay, then we have to show that f is 1 1. Basic. How do we do 1 1 in your class 12th examination? What do we do? If x comma y be two element, okay, and f x equal to fy. What do we do? In any of the theorem in class 12th or in your higher studies, what do we do is, if I write fx equal to fy, then if we show that x equal to y, then we can say that it is 1 1. So here also we will do the same thing. I told you, I have always studied mathematics and taught mathematics with basic understanding, basic definitions, using those basic definitions. I don't believe in techniques and tricks. I think that the basic definition would help you to get whole clear understanding of mathematics. And those who are not good at mathematics, that in your intermediate level or your 10th level or your graduation level or in this UPSC, is because they haven't understood the concept. If you get the clear grasp of the concept, basic definitions, you can easily do that. Okay, so I say fx minus fy, or I can say that fx minus fy is equal to 0 dash. I have taken this here. This is equal to fx minus 0 dash. How come this? Since f is a homomorphism, we can take this inside it. So we can say that x minus y belongs to kernel f. But it is given that kernel of f has only one element, that is 0, which means that x minus y is equal to 0 or x equal to y. Hence proved f is 1 1. Our theorem is proved. This theorem has immense use, I would say immense use in linear algebra, in linear transformation, in everywhere. So in fact, you have to use this theorem by heart. Okay, in any case, in modern algebra, in linear algebra, it is shown that if you ask that, show that this is 1 1, all you have to do is show that kernel of f is 0, contains 0 only element. Okay, in the future you will also see that this is the condition for onto also, but that would be a topic for different day. But for now, I think this is very clear that these two theorems are very important. That first of all, kernel f is an ideal of R, okay, and kernel f is 0 if and only if f is onto. I hope this topic is a bit tricky and conceptual, but I hope I made this easy for you. And if you have any problem regarding this, you can write it on YouTube also, comment section also, and I'll hope that I'll solve your queries. Okay, thank you.